In this session we will see the minimum and maximum mode 8086 signal description. So this is the pinout of 8086. 8086 processor is a 40 pin package. There will be 40 pins in 8086, and many of the pins, right, they have common roles in the minimum and maximum mode of the processor. So what you should understand is this processor 8086 can work in two modes, minimum and maximum. In minimum mode, 8086 alone will be the processor available in the computer system, while in maximum mode 8086 is capable of working with other processors or along with a coprocessor. A coprocessor is a chip which performs dedicated computation like floating point computation. So it means that 8086 can be coupled with a processor that can perform floating point computation in maximum mode, or it can be coupled with other 8086 or 8088 processors for enhancing the speed of the computer system. So that is known as maximum mode. So as I was saying, in minimum mode there will be certain roles played by certain pins which are written here in case of pin numbers 24 to 31. So in minimum mode, the pin numbers from 24 to 31 will be performing the roles given in these brackets, while in maximum mode the pin numbers from 24 to 31 will be performing the roles given close to these pins. Okay, so we are going to examine that in detail. So as I told you, based on the working configuration, right, the pins, the 40 pins available in 8086 can be divided into these three categories: the pins that work in both minimum and maximum modes, or the pins that perform same role in minimum and maximum modes. Okay, then the signals generated by the pins which are available only in minimum mode, then signals which are available only in maximum mode. Okay, so there are three types of signals that you can see in 8086. The signals common in minimum and maximum modes, signal present only in minimum mode, signals present only in maximum mode. Let's first see the signals common in minimum and maximum modes. Okay, so this table gives a comprehensive list. So the first set of signals are AD0 to AD15. Okay, so AD0 to AD15, they are the address data lines. Okay, they are address data multiplex lines. Both address and data flows through this line. Then they are bidirectional lines, and they are tri-state lines too. We will see what that means. So if we see AD0 to AD15, it means you can see here, right, AD0 to AD15. So 15 is here. So they are multiplex address data lines and bidirectional. Okay, so the first thing, multiplexed line means that both address information or address bits as well as data bits are communicated through these lines. Okay, and these lines are time multiplex. That means at any point of time, either address or either data will only flow through or flow in to these lines. Okay, suppose that we will consider a case where we are just only transmitting address through these lines. So it means that we will have a 16-bit address across these pins from pin number 16 to 2 and in pin number 39. Okay, and these pins at that time when it is transmitting address value alone can be named as A0 to A15. Okay, then suppose that at some other point of time, if these pins are transmitting data alone, either as input or output, we can name these pins as D0 to D15. Okay, now one more thing, we know that in 8086 the address can be of 20 bits in size, while the registers are of only 16 bit size. Okay, so these 16 address data multiplex pins are not enough to show the address values. We need 4 more pins, right? So those pins are A16 to A19. Okay, you can see A16 to A19 pins over here. right? That is in pin numbers 38, 37, 36 and 35. So those pins are again multiplex, but they are multiplexed with status bits alone. They don't have data bits. Why? Because in case of 8086 it has only 16-bit data capacity. Its address capacity is 20 bits. So the upper 4 bits of the address is provided from pin numbers 38 to 35 as A16 to A19. Okay. So what we have learned from this section is we have address data pins multiplexed from 0 to 15 and address pins multiplexed along with some status pins from 16 to 19. Okay. So we will see what are the uses of these status pins. Okay. And we just saw that the status pins multiplexed with the address lines are S3, S4, S5 and S6. Okay. So S3 and S4 together will indicate for addressing which of the base registers or segment registers are currently used by the processor. Okay, so if the code given by S3 and S4 together are both zeros, it means it's an extra segment. If it is like this 0 1, it means it is a stack segment. If it is 1 0, it is a code segment, or it can be nothing. And if it is 1 1, it is a data segment. Okay, so S3 and S4 together will give us an idea of the base segment register which the CPU is using for addressing. Then the S5 bit indicates the status of the interrupt enable flag. Okay, what is the status, whether interrupts are enabled or disabled, which we can see that through S5. Then the pin number S6 is always set at 0, and it indicates that 8086 is the controlling master of the bus. Okay, so these are the meanings of the pins from S3, S4, S5 and S6. So once again about AD pins. AD pins are bidirectional, which can take data into the processor and outside the processor, and AD pins or address data multiplex pins can take address or data at any time. At a point of time, it can either take address or it can either take data. Note that the pins above 15 are only address pins from 16 to 19, and they are multiplexed with status bits indicating the base register which is used for addressing. Okay, now we will proceed to the next common signals. We have BHE, minimum maximum mode signals, and RD, right? We have a BHE, minimum maximum mode, and RD. So what can be minimum and maximum mode pins? Minimum and maximum mode pins will give you an idea whether the processor is working in minimum or maximum mode, and it is an input pin. It means that you can give either a active high input to this to keep the processor in minimum mode, or you can give an active low input to keep the processor in maximum mode. Okay, you can set the working of the processor. Then what is the purpose of read signal? The read signal is an output signal, or it is a signal generated by the CPU which indicates that the CPU is currently performing a read operation. Okay, so that's what is told here. We have MN MX pin, right? What is the use of MN MX pin? MN MX pin is the pin number 33, which is used to set the processor either in minimum mode or maximum mode. Okay, then what is the use of RD? RD is a signal given by the processor to the outside interface, showing that the processor is doing a read operation. Okay, then there is one more signal known as BHE. Okay, pin number 34, which is bus high enable. Okay, it is multiplexed with a status pin S7. So what is bus high enable? Bus high enable is a output signal, or it is a signal shown by the CPU to the outside peripherals or interface circuit, saying that currently data is being supplied from the upper 8 bits of the data lines. We know that in case of 8086 can output 16 bits or 2 bytes at a time. Okay, so whenever the upper byte or the bytes from pin numbers D8 to D15 or the bits from the pin numbers D8 to D15 are being output by the CPU, BHE will be active. And one thing to be noted here is BHE is active low. So when D8 to D15 are used for data transmission, BHE will be low. Okay, logical low. Okay, that's the important thing to note here. Okay, now we will move to the next common signals. So next set of common signals are test and ready. So we have test and ready in this chart, and you have to note that test is active low and it is an input signal. Okay, and ready is an active high signal, and again it is an input signal. So we will see what these two input signals are used for. So what is the use of test signal? Okay, test signal is used in combination with a particular state of the processor or instruction of processor known as the wait instruction. The wait instruction will actually suspend the execution of the CPU, or it will make the CPU wait for a particular impulse or stimulus from the outside world, and that stimulus has to be given from the test input pin. You can see the test input pin at number 23, right? So suppose you have a instruction executing wait, CPU will wait till this test is depressed to active low by an entity from outside the CPU. Okay, so that is the use of this test input pin. Now next pin is the ready input pin. Then what might be the ready input pin? A ready input pin is actually a pin used by slower devices which are performing or which are participating in a memory transaction, and it is used by those devices to intimate the CPU that it is ready or it has completed the data transfer, and it is an active high signal, and it is given at pin number 22 to the CPU. Okay, now we will see what are the next set of common signals. Okay, we have NMI. Okay, we have an NMI signal which is common across minimum and maximum mode. And what is NMI? NMI stands for non-maskable interrupt request, and it is the input signal pin. Okay, so it is pin number 17. So what is the use of pin number 17? It is used to indicate or warn the CPU that a non-maskable interrupt case has occurred from outside the CPU, and CPU should respond to it immediately. Okay, so depressing the NMI or activating the NMI pin will cause a type 2 non-maskable interrupt to be issued within the CPU, and it is a high priority interrupt, and it has to be serviced immediately. Note that NMI pin can't be masked. Okay, it can't be turned off by using any of the methods. It has to be serviced definitely. So that is NMI signal or the NMI pin. We will see what are the next set of signals. We have reset, clock, and interrupt request. Okay, we have reset, we have clock, and we have interrupt request. What is the use of reset pin? Reset pin is an input pin, and it is used to reset the system. Okay, then what is the use of clock pin? Clock is again an input pin. It will coordinate the activities within the CPU. Then what is the use of interrupt pin? Interrupt pin is an input pin. It is used to issue an interrupt request. Okay, so those things are written here. Note that interrupt pin is actually a maskable pin. If you turn off the interrupt enabled flag within the flags register, this interrupt pin will be turned off, or this will be deactivated. Okay, no other device can request interrupt through INTR pin. Okay, so that is a gist of all common signals. Then we have two more signals or two more pins which are used in the common configuration, that is VCC and ground. Okay, obviously we know what is VCC, right? VCC is used to supply voltage, working voltage to the CPU. It is pin number 40, and the working voltage is plus 5 volt. And ground is used to provide grounding or to complete the circuit in case of the CPU. Okay, it is pin number 20. Minimum maximum mode pins we have seen. It is either it is used to put the CPU either in minimum mode or maximum mode. Note that minimum mode is the uniprocessor environment, maximum mode is the multiprocessor or the coprocessor configuration. Okay, now let us see what are the minimum mode signals. Okay, note that the signals given in this table work only when the minimum maximum mode pin is set as VCC, or when the minimum mode is triggered. Okay, or this configuration is used when your 8086 is controlling the memory and IO bus. Okay, so we will go through the duties of all these signals individually. So the first one is hold and hold acknowledge. Okay, so what is hold? Hold is input pin. Hold acknowledge is an output pin. Okay, so what is hold? Hold is actually a signal given to the CPU by the external bus masters or controllers to request the CPU to leave the control of the bus, okay, or the system bus, okay. Or so actually what it means is that whenever some external bus controller or a bus master needs the control of the system bus, it will request the CPU through pin number 31, that is the pin hold, that I need the bus, can you please leave the control of the bus. So CPU, if it is going to grant or accept or consider the request, it is going to issue a signal through HLDA or pin number 30, indicating that I acknowledge your request, you can now take the bus, okay. So 31 and 30 work in tandem. They are actually used for communicating with the peripherals or other bus controllers regarding the control of bus, okay. Now the next set of signals are the remaining one, that is write memory bar IO, DT are done or data enable, ALE and interrupt acknowledge, okay. WR stands for write control or write, M bar IO stands for memory or IO, then DT bar R stands for data transmit bar receive, DEN stands for data enable, ALE stands for address latch enabled, INTA stands for interrupt acknowledge. So note that almost all the pins are output pins, or it indicates some signals being sent from the processor to the outside world, right? We will see what is the meaning of these signals. So what is the meaning of DT bar R or data transmit receive? Note that it is a minimum mode configuration, so your CPU is in charge of the system bus, right? Or it will generate the bus control signal. So actually all these things are bus control signals. So what is data transmit receive? Data transmit receive indicates actually the direction of data transfer, okay. We know that the data lines or the address lines are actually connected directly to buffers, right? And these buffers are bidirectional, okay. We know that AD lines are bidirectional, so either they can take data or address out of the CPU or can bring data or address into the CPU, okay. So the direction of the transfer has to be told particularly to the buffers, then only they will conduct it in the proper way. So that is told through this signal DT bar R. So if DT is positive or if it is active, it means that the CPU is giving data outside, okay, to the outside world, or AD lines will be pushing data away from the CPU. Suppose that DT bar R is negative or active low, it indicates that the CPU is now trying to receive from the outside world, or the address data lines are going to bring contents into the CPU, okay, or the buffers are supposed to transmit the contents that they are having into the CPU through these multiplex lines. So that is the meaning of data bar R or DT bar R. Now what is the meaning of DEN, data enable? Again, these transceivers or buffers, actually buffers are known as transceivers. These transceivers or buffers are actually tri-state gates, okay. We have studied that in computer organization and architecture. So in order to enable those buffers to conduct in any of the directions, the DEN signal has to be active, okay. So when the CPU is ready to transmit or receive data or address through the transceivers, DEN will be enabled, okay. Then only the buffer movement is possible. Then what is the use of ALE signal or address latch enable? It is used for address transmission. Note that the address data lines are multiplexed up to 16 bits, right? So address and data can appear in those lines. So the outside peripherals, if they are demanding address, right, then they should get address alone, okay. So what happens is they should actually be intimated when the CPU is transmitting address, when the CPU is going to transmit data through the multiplex pins. So this ALE, address latch enable pin, or the signal will give an indication to the outside world when the CPU is going to transmit address through those multiplex lines. So when the CPU is going to transmit address through those multiplex lines, ALE will be active, okay, or ALE will be high, and ALE can in turn be used to trigger the latches which are used to send addresses or used to receive addresses from other device. So address related operations are actually triggered using ALE, address latch enabled signal from the CPU, okay. That is use of ALE. Then the next is M bar IO. It means that memory or IO. So CPU's memory or IO operations are distinguished using these signals. Suppose that CPU is going to access, that is either read or write to a memory location, then the pin number 28 or memory bar IO pin will be high. Suppose CPU is going to access some IO device through some ports, then the M bar IO signal will be low. Okay, so that's use of M bar IO. Then we have a write signal. It is used to indicate that the CPU is going to perform a write operation, and it is an active low signal. Then we have an interrupt acknowledge signal, again, which is an active low signal at pin number 24. If a maskable interrupt source issues an interrupt request to the CPU, and if the CPU is going to accept that interrupt request, or if the CPU is going to initiate ISR, then interrupt acknowledge signal will be triggered. Okay. Now we will see what are the maximum mode signals. Note that maximum mode can be triggered by setting the MN bar MX pin to ground, okay, or making it low. And these are the list of maximum mode signals. We have a request grant access control signal, which is bidirectional. We have a lock signal. We have some status bits also. Note that in maximum mode, the processor works along with other processors, or in a multiprocessor environment, or with a coprocessor. So what happens is the bus will be in control of a bus controller, okay, like a 8288, and so the processor's intention, right, it is indicated through many status bits. So if you see this list, majority are status pins or status signals, and these status signals will cause the bus controller to initiate the corresponding system bus signals for memory and IO. That you have to note mainly here. Okay, so in maximum mode, the processor won't be creating or issuing the bus control signals. The processor will be issuing some status bits, and those bits will be read by a bus controller, and the bus controller will be issuing the memory or IO bus signals. Okay, we will see individually what are those. So the first one is request grant bidirectional pins or bidirectional signals. Request grant signals are used by the external devices to request the control of the bus from the processor, and to get the status of the request from the processor. Okay, and there is a pair of request grant signals, okay, at pin number 30 and 31. And note that request grant 0 is at 31 and request grant 1 is at 30, and request grant 0 pair has a higher preference than request grant 1 pair. Okay, so suppose a device places a request for the system bus at pin number 31, and suppose another device places a request at pin number 30. The person or the device which placed the request at 31 will be given preferential treatment by the CPU. Okay, and how will the CPU indicate that it is ready to transfer the control? It will issue a bus grant signal from the same pin. Okay, so bus request bus grant signal or the pin is used to request to the CPU to get control of the bus, and by the CPU to indicate to the devices that it is going to grant control of the bus. Okay, then then we have a lock signal. Okay, so what is a lock signal? Lock signal is actually an indication of execution of a lock instruction. Okay, so in case of 8086, certain instructions can be prefixed with a lock attribute or lock keyword. And what is this lock keyword? The lock keyword actually ensures that the instruction that we are executing is going to be atomic. Suppose that we are going to perform a move to a memory location or read from a memory location, and to that instruction we are prefixing lock. So what it means is that that instruction will be atomic, or no other bus masters or devices will try to get control of the bus from the CPU when the CPU is executing that particular write or read. Okay, so that is the use of lock keyword. And what is the use of this lock signal? This lock signal is actually an indication to other devices that CPU is executing such a locked instruction or an atomic instruction, and other bus masters should wait or should not request for the control of the bus when the instruction is getting executed. Okay, so as long as that instruction is getting executed, or that lock prefixed instruction is getting executed, this lock signal will be active or active low. So after the signal is inactive, maybe the others can request for the bus. Okay, then we have seen lock. Then the remaining thing is the status bits S0 to S2, right? There are 3 status bits, and as I told you, these status bits are used to give an indication to the 8288 bus controller which all memory or IO bus signals has to be generated. Okay, suppose that all the status bits, right, from S0 to S2, right, S0 to S2, that is from pins 26 to 28 zeros. It is an indication to 8288 bus controller that you issue an interrupt acknowledge signal on behalf of the processor. Suppose that the processor wants to tell an IO device that it is going to perform a write to operation, right, to through 8288 bus controller. What it does is it will put this pattern, that is 0 1 0, and what happens, the 8288 controller will issue the IO write signal, okay, instead of the CPU. Okay, so we are having a bus controller as an intermediary in maximum mode to issue signals on behalf of the processor for the memory and IO devices. That's the most important takeaway from here, okay, or from the maximum mode. Then we are left with 2 bits, that is QS0 on QS1, right, in pin numbers 24 and 25. And again, these are used to indicate status of the processor with respect to the prefetch queue. Okay, we know that in case of 8086 processor, within the bus interface unit, there is a prefetch queue which will prefetch the instructions and keep it so that it can be pipelined to the execution unit, right? So the status of the queue can be read by the external devices or other coprocessors or processors by scanning the pins 24 and 25. We will see what is the meaning of the combined signals. Suppose if QS0 and QS1 are both zeros, it indicates that no operation or no instruction is pending within the queue. Suppose it has the pattern 0 1, it means that currently the first byte of opcode has been read from the queue, okay, or from the queue 1 byte opcode has been taken into the execution unit. If the pattern is 1 0, it means that the queue is empty, or the instruction prefetch queue is empty. And if the pattern is 1 1, it means that we are going, or the CPU is going to take the subsequent byte from the queue. So let me just tell you what this code means with this diagram. So suppose that this is your instruction prefetch queue, okay, so this will be the rear of the queue facing the memory unit, and this is your front of the queue facing the CPU. Okay, assume that we have a instruction here, okay, so the instructions opcode will be here, data will be over here if it's a 1 byte opcode instruction. There are certain instructions which can have a multi-byte opcode, so it means that opcode will be partially here as well as in the second entry, and data will be in the third entry. Okay, so the prefetch queues working will differ based on the length of the opcode in each instruction and length of the operands in each instruction. So we will see how. Suppose that first we are going to see an instruction with a single byte of opcode. Okay, so if we have a single byte of opcode instruction, what happens is this area, suppose that it is 1 byte, okay, suppose that this is entire thing is 6 byte, okay, that is the length of the queue, right? So this is the first byte, so our opcode will be here, then this is the second byte, here our data will be here. So the decoding unit will first decode the first byte, it finds that it is an opcode, then inside the opcode or scanning the opcode to know whether this is a full opcode or it is a partial opcode. And if it is a full opcode or if it is a 1 byte opcode, what happens is we should execute this instruction, right? So the operands will be immediately following the opcode, so the instruction can be taken from here and can be executed. Okay, on the other hand, suppose we have a multi-byte opcode, so when this first byte is decoded, immediately the execution unit will know that still remaining parts of the opcode are pending in the queue. Okay, so from the second byte of the queue, the remaining portion of the opcode will be taken, and what happens, it will be decoded, and as usual the operand will be in the third byte, and the operand will be taken and the instruction will be executed, and correspondingly the queue movement will happen, right? That is, from the rear the elements will be further moved to the front, and when the rear will be free, other instructions will be prefetched and brought into the queue. Okay, so this is how it works. And as I told you, the queue will have various status at various points, right? So that is indicated through these status bits. Okay, when the queue is entirely empty, what happens? It will be 0 0. When 1 byte of opcode is read from the queue, right, what happens? 0 1 is the indicator. When the queue is empty, it is 1 0, and when a subsequent byte is being read, right, like this, this will be the pattern. So this is the minimum and maximum mode signals and working of prefetch queue in case of 8086.